let's go to the lab. The software lab, the 2-week lab over here. Click lab 8. I was trying to add more explanations to the assembly code, and I was looking at the main part of it, which is a multiplication assembly. So today we're going through all the register states of the, I think it's only 3 multiplications, and the quiz today is regarding the assembly code over here. I'm gonna give you different examples, different numbers. For example, just the two different binary numbers multiply for multiplication, and I'm asking you to list all the states of the registers. So at which register? It's basically just running all the instructions in your mind and write it down so you can understand how these carry bits are working. I know this could be challenging, but I'm doing one example for you now, and you are allowed to make notes and look at the notes after that. But eventually they will be different numbers. Okay, so through this process, we'll be able to understand a lot more details about all the instructions, like the shifting, the carry bits, and the jumping and return. Okay, so this is the only example, assembly example we're going to practice today. And after this one, we'll get into UART, the UART protocols. And the Tuesday after spring break, I'm going to start looking into more details of the assembly code for the square problem of the 2-week lab. So there are more sections that are worth some explanation. Okay, let's take a look. So this one has all the loading. There's an index. There's a loop. You can see the multi-loop also exists over here. So whenever this is not completing the entire all the shifting yet, it's gonna jump back to here. So it's forming a loop by itself because it doesn't like the Arduino's. You have a loop function. It's looping from the end to the top by itself. So this one doesn't have that sort of mechanism. Eventually, you have to jump, right? Have to jump to somewhere and use the index. So this can be, you can define the number of jumps, the number of loops by itself. Okay. So the way to do that is using the index. You can see the index, the I here, initially was assigned a value of 8. So which means this is shifting by 8 times. So you can see every time it enters here, it's doing a subtraction. So subtracting 1 from 8. Okay, if it's non-zero, it's not 0 yet. It goes back to multi-loop. So we'll go through the details about the shifting and the loop in a bit. But now you know that this loop will run for 8 times. Okay, and whenever it's 0, it returns probably to, let me see, where it jumps, right? So where it starts jumping, it returns to that place. So eventually it will be done, but actually it doesn't matter because after all the shifting, all the numbers are zeros, so it's not really doing anything anymore. I believe this return is a return somewhere else in the assembly code. So it's not going back to the top anymore. But this is just a part of the assembly code. There are a lot of other sections we'll go through. Okay, but let's just look at this one for now. Take a look at the tutorial. If you can open up another tab over here, go to the tutorial of the software in the class tutorial. Click software link. You'll see the details about the shifting. So take a look at S0. So what is S0 doing here? So the in-class exercise is about UART. Okay, it's not assembly code programming. Assembly code programming will be a quiz after we go through the details over here. And the in-class exercise is 0.9 points, bonus points. And after assembly code quiz, we'll start looking for the details of the UART communication. Okay, not right now. So you don't have to use the in-class exercise for now. Just pay attention to the instructions. So SR0 is shifting all the bits to the right by 1 bit, and the LSB goes to the carry flag, and 0 got moved to the MSB of the register. So that's what SR0 does, and it's changing the register's data by itself, and so that means whatever was stored in the register will be replaced by the new one, which is got shifted, right? And the C will be updated as well. So C is shared, right? It's a universal flag. It's being shared by so many different. Is there just one C? Okay, just one C register bit. So sometimes you got a C after one instruction, but eventually, if you do a adding operation, and the C will be replaced. Keep that in mind. So in that case, let's go back to the code over here and go through all the steps. And let's see if this makes sense, all right? We have to use two numbers, multiplicand and multiplier, as one example, to go through all these. So if we are doing 111 times 101, for example, okay, how do we do that? Pretty easy, right? So 1 times all ones, 111. Yeah, I know these are 8 bits, but I'm just using the lower 3 bits for now, which is okay because all the rest are zeros. It's over there. And next, 0 times all the ones are getting zeros, right? But shifting everything to the left. And then 1 times all the ones, and you add all of them together. 1, 1, 0, 0, 0, 1, right? That's the final result. So we need to create a code, assembly code, to do the same thing, result in the same product over here. So now let's look at the assembly code over here first. So whenever this is getting started, you should know that S4 is the multiplicand, S3 is the multiplier, right? And I'm using S5 to store the upper bit of the product, and S6 is the lower byte of the product, which is fine because it's just 2 bytes, right? It's just 2 bytes. So whenever it enters here, the first thing is loading a 0, all zeros to S5, just to clear all the bits in S5. So I6 still doesn't have anything in there, right? By default, it should be 0, but we don't have to write it down for now. All right. So this is the index. Index is loading an A into it. So something running behind the scenes like a counter. Yeah, because it's subtracting 1 from 8 every time. So eventually it runs for 8 times until it reaches 0, will return to the previous location before it enters the top of the multiplication code. Okay, so we don't have to worry about this one for now. Then it enters the multi-loop. SR0, S4. What is this doing? Go back here, take a look. So S4 is a multiplier. The shifting everything to the right by 1 bit. So the LSB is shifted to C, right? Shifted to C. Why this helps? Because every time you are doing the multiplication, you are checking. Wait, S4, S3. Let me see. Give me a second. S4 seems like S4 is a multiplier. Yeah, sorry. So let's keep it consistent. So S3 is a multiplicand, S4 is a multiplier, right? Then it's shifting the LSB of S4 out, so eventually you know the C, which is the LSB over here, which is basically this bit, right? S4's LSB. It's getting shifted out. So if you notice this is 1, you are putting a 1 here, right? You are putting 1 times everything as basically as 3 over here. If it's 0, if you are shifting out the 0, 0 times everything is 0, you're just getting a 0 here, right? So that's why we want to take out the LSB of the S4 every time. So we know which should be multiplied to S3. Does that make sense? So S4 is a multiplier, okay? Every time we are doing multiplication, we are basically use each bit in here times every single bit in the multiplicand, right? So that's why we want to take out every single bit in the multiplier each time, so we know what we want to put in here as a result for each step. Okay, so the first time we shift S4 to the right, and 1 is getting shifted out. So 1 will be moved to C because of this instruction. Okay? This instruction does it for us. So C becomes 1. Okay, if you come back to the code, it's non-C. So if C is 1, you directly do an adding, right? You do an adding. You add S3 to S5. So S5 is the output, is upper byte of the output. No worries, since everything will be shifted to the right by 8 times. So now it's just if it's non-C, which means if the LSB of S4 is not 1, then it will directly jump to this label here and run all these shifting, which we'll go through in a bit. But if it is C, it's going to add S3, which is a multiplicand, to the upper byte of the product. Which makes sense, right? So now, after the first step, we know that S4, the LSB of S4 is 1, right? So eventually, we should add the next instruction being executed will be this guy, because it's not non-C, it is C. C is 1, so it's adding S3 to S5, and S5 was 0. So eventually you're adding 111 to this register. And what is the result? Because this is the 1, so you're adding 1 of 111 to S5. It's adding to the lower byte, lower 3 bits. Okay. What's next? I have a really quick question for you guys. It could be on the quiz later, okay? So for now, after this line of instruction, what is the value in C now? What is the state of C? After this one, what is in C? You're lost. After this one, what is in C? Shift 1, yeah, shift S4 to the right by 1 bit. So this LSB is shifted to C. So C is 1. Okay? Keep in mind. So, what about this one? After this, what is in C? Is it doing anything to C? There's no carry, right? So carry 0. So C will be cleared. Has to be cleared. Okay, that's good. Eventually you'll find out that has to be cleared. So C becomes 0 after this one. So what's next? SRA, right? If you look at the code, what's the next one should be executed? So after the adding, it's not shifting, it's not jumping to anywhere, so it should follow the sequence here. It's gonna execute this one, SRA5, SRAS5. SRAS5. Now let's look at SRAS5. SRAS5. Where is it? I think I put it here, maybe. Yeah, I found out a very good explanation from the study guide or user guide over here. So SRASX shifts the previous state of the carry flag into the MSB. Keep in mind, at the same time. At the same time means what? So at the same time, the carry flag is loaded with the LSB. They happen in parallel at the same time. So that means the LSB, when LSB is being put in C, and the previous C got loaded to MSB. Think about that. There's a register, right? SRA to this register, what's being done is, because C is a universal bit, it's already existing, so whatever in C previously before the shift will be put into the MSB at the same time. The LSB of the register is replacing the previous C in C. Does that make sense? So you are not loading the LSB to MSB, so it's not shifting back. The LSB got shifted to C, and the previous C got shifted to the MSB. That's how that works. And everything got shifted to the right by 1 bit. You know what I mean? So the previous C is replacing the MSB, and the previous MSB is shifted to the second bit over here. You are not losing it. You are not losing the previous MSB. It's just everything got shifted. Are you losing the LSB? No, the LSB goes to C. Okay? So everything got shifted to the right, and the MSB is replaced by the previous C. Okay? And then now let's look at the code here. I think it's still in the same page. This one. So whenever SRA S5 is being executed, what's really happening by looking at this chart? By looking at this one, what is happening? What is happening? S6 is not getting, no value was assigned to S6, which means whenever a register is getting instantiated, it should be 0 in S6. It's probably getting cleared somewhere else, but now we don't see anything about S6 by far, so S6 should be 0 at the very beginning. So in that case, I'm shifting for this line of code, right? You got a C bit in the middle. So this instruction is shifting everything to the right, so this one goes to C, and the previous C after this line was what? I just told you. 0. Okay, so 0 will be put in the MSB of S5, and everything got shifted to the right. So how many zeros tell me before we put 1s over here? How many zeros? Are we losing the MSB? No. So how many zeros? 5. Just count. 1, 2, 3, 4, 5. How many 1s? Only 2 bits left. So where's the other bit? Here. So everything got shifted. LSB goes to, so draw a little arrow here, goes to here. What is in S6 for now? Okay. What about next? Same instruction, right? But different register. Is there anything to do with S5? Nope, just copy. Is there anything to do with S6? Yes. What's happening? Shift C, remember the instruction, what the ISRA instruction does? What this instruction does is it's moving the current C to MSB and at the same time, keep in mind, at the same time, moving LSB to C. So let's just get another C here, but you should know that it's the same C, okay, it's the same C. Zero. So eventually you are getting 1 0 0 0 0. That's just all zeros, right? 7 zeros and 1. What's next? What's that?
So is every C like in between the S5, S6, like?
It's the same C.
I mean, like, is there like a C in between, like S1, S2?
No, it's just a universal C, just one bit.
Okay.
It's magical, right? Here's one C in the whole circuit. So every time it changes, it's going to be overwritten, right? So now it moves to the subtraction. It was 8, right? It was 8. So 8 minus 1 becomes 7, right? So it's non-zero. Non-zero jumps back to where? Here. Okay? Job is not done yet. Keep doing the same thing, okay? Let's come back and do the same thing here really quick. What's the next instruction? What is the value here for the next bit? 0. So 0. What's the next if it's 0? So it's non-C, right? So carry is 0. Carry 0 so it's not 1. So not 1 means not C, okay? It's not C. Don't do the addition, which makes sense, right? It's a 0, you're not adding anything to it. So directly it goes to shifting. Just not adding anything, but shifting. Okay? So shifting S5. Shifted. Nothing to do with S6. But it's followed by this. Is SRA instruction changing, replacing, or losing any bits? No, it's just everything getting shifted. Are you losing this one for S6? No. So this one will be shifted. So we're getting 2 1s. Okay? Where's the current C now? I should have. I can label it here, it doesn't matter. It's just the same C. So what is the C now? 0, right? Still 0. Okay? And that 0 will come back to SRA5 next time. So it's actually replacing. No, it's being overwritten by SR0, S4. Because this is being executed before this SRA S5. So this C is really not doing anything, right? This is being overwritten by 2 in the sequence. Does that make sense? Even though it's doing a C here, but it's not doing anything. This C is being overwritten immediately after. So then move to this instruction here. It's a 6, still not 0. Come back and do it one more time. SR0, S4. They are getting a 1 again. They're getting a 1 again. Right? So that 1 is giving you what? That 1. It's giving you a C. So eventually it goes to the adding instruction. So you have to add 0, 0, 0, 0, 0, 1, 1, 1 to it, right? You have to add to it. So this was in S5. You're adding S3, which is the multiplicand, to the S5, the current S5. So just do addition here. Eventually you're getting 0, 0, 0, 1. Is there carry out for the byte? Is there carry out? No, no carry out. So C becomes what? 0. This is add. Then it moves to SRA5. S5. So this is what is in S5 now, right? And S6 is still having 1, 1, 0, 0, like this. Then you find out this is super delightful. You feel happy. Why? Look at this result. Compared to where? Yeah, shows up. But it's in the middle. It's in the middle, right? It's in the middle. So you'll know that this index is still not 0 yet. So it's still gonna shift everything to the right. And the thing is, the multiplier, all the 0 bits in front of it are all zeros. So whenever after shifting this MSB of the multiplier out, all the following multiplier bits will be all zeros. So it's basically not adding anything to it. So whatever this guy is doing is just shifting, just purely shifting. It shifts the LSB to C and get that C to the MSB of the lower byte, and eventually just everything got shifted and using the C as a buffering bit, but nothing else. So it's gonna shift for how many times after this? For how many times after this? 6 more times, right? It's gonna shift it for 6 more times. So shift, you can see count for the zeros over here is basically 6 zeros. And eventually shifting for six more times will shift everything to the lower byte. And that's the final product of the multiplication. Okay? Does that make sense? So the bytes are still bytes. Nobody tells you that byte must be the upper byte. This must be the lower byte. Nope. It's just you're just whenever you are using the 2 bytes, combine them as one number. You do a concatenation, or you do a little bit of operation in there to make this one, to force this one to be the upper bit. So how to do that? I mean, just curious. I mean, in C is pretty easy, right? Everything is running behind the scene, but in assembly you have to handle the register level operation. You don't have to do anything, right? Just treat them differently. When you are treating this register, you just have to treat it as an upper byte. But eventually these are all filled up with zeros, but just in case you have ones in the upper byte, just treat it as the upper byte. You treat these as the lower byte. So whenever you are seeing a 1 here, it has to represent a certain number at that digit. Is there any question on this? No. So you can make notes. You can look at the notes when you're doing the quiz. I'm going to give you a few minutes to study this after the UART instruction lecture. Okay. Any question on this? Let's move forward. So I think these are the two most exciting tutorials in this class, because you guys are making a universal communication port, and which is able to communicate with standard commercial devices like Arduinos. And so the examples in this class, in this tutorial, is letting you make a UART communication port, and that port from the IPGA board is able to directly communicate with the USB port of the laptop, because the laptop's USB is basically a serial. There's a serial converter chip on the IPGA. It is able to convert the USB communication to standard RX and TX signals. And eventually, if you open up a terminal, like what you did in the Arduinos, remember the, what's that called? Terminal? Serial terminal, right? Serial terminal can plot and do a serial reading. Let me show you. It's really familiar. You must be very familiar with that. See, like this, right? You have seen this a lot, right? So this is just one of the serial ports or sort of serial terminals can use. But there are so many different variants available on the market, and they're free. So the one we will use for another task is called I couldn't even remember the name of it. Terra Terminal. I think there are other terminals like what's the name of the other one? Really popular. I can't remember. So download this one, but you are free. Feel free to use other versions of serial terminals. So these are just terminals you can open up in your Windows operating system, and you can change the port number. You can change the baud rate, which is something we'll talk about in a bit. You can change the parity bit, all these kind of parameters. And that commercial, keep in mind, so there's a TX and RX module. It's a digital block being designed by whoever designed your laptop or desktop. Okay, so right behind that USB port, there is a RX and TX module. Okay, if you follow the standards, because the UART protocol is a standard, if we follow the standard to program our UART module in IPGA, and they will be able to talk with each other, communicate with each other, which is amazing. So let's go to the top and look at the protocol of the UART. Okay, so question number 1. UART transmission starts with what? Stops with what? So you can see the UART transmission is really simple. Okay, if I'm drawing a diagram for you guys, you can see if you're having Arduino or ESP32 or any kind of microcontroller, you'll see that there will be a RX and TX port. Okay. And these ports are being used for different purposes. You can use TX and RX for communication with sensors, or you can use TX and RX for getting the C program from the laptop or desktop. So looking at this application is connecting RX of the Arduino to the TX of the sensor. So for example, you are designing a digital sensor for the course project, and you want to use a UART as a communication port. And so you will have a TX, it's a physical pin of the sensor, digital pin. And there will be a RX as well, so you got 2 pins. So for serial or UART, it has only two ports, right? Only two ports. One is TX, one is RX. Just one bit for each. So they communicate serially. If you look at this one, it's just one line. If you have a sender on the left, and you have to have a receiver on the right, so which means the sender is sending to the receiver. That makes sense, right? So TX to RX, RX to TX. Keep in mind. It has to be this, okay? And it just because there's just one line, right? There's just one line, just one metal piece, one voltage node. If the transmitter put it down to ground, the transmitter decides to put it down to ground at the moment. RX will see it, right? It's just one wire. I put it down here, you'll see it getting put down to ground. So the receiver will receive a 0 as well. Make sense? Same thing to the other direction. So if the sensor put it down from the TX, the RX will see it. Okay, so the answer for the first question is, it starts with the transmitter pulls the voltage, pulls the wire down to ground. Pulls the voltage down to ground. So that's a start bit. It's a start bit, a 0 bit. So the transmitter pulls it down. So the receiver knows, okay, so after this 0 bit, I'm gonna receive data. Make sense? Okay. The digital signal can run at any time. It's just oscillating 1010s, right? I mean, they don't have other languages. There's no like English happening, right? The sensor, Arduino is telling the sensor, hey, I'm gonna start right now, okay? They cannot talk in that way. So basically, they have to communicate in a certain protocol. They have to follow a certain protocol. So now here's the protocol, which is the transmitter. Put it down to 0. Okay? So it starts the talk, starts the communication, and followed by the start bit. It comes with the LSB, the 0, D0, and then D1, D2, and eventually D7 for the whole byte, for the entire byte, and then followed by the parity bit. Remember how we generate the parity bit for the sender? Yeah, XOR, right? Okay, so you can have a parity generator in your transmitter module and just put it into a concatenation, the curly bracket. You can directly force it to be the parity bit. We'll see the code in a bit, okay? So anyway, so you are able to do that easily. So put that parity bit with your data byte as a package, and eventually send everything out bit by bit. And whenever all the bits are sent, you should stop it. So it's getting stopped by the transmitter. Okay, the transmitter does it. Keep in mind, not the receiver. The transmitter pulls it up to 1. Okay, this could be a really common interview question, right? What is the starting bit and ending bit of the UART transmission, UART communication? So starting with a 0 and end with a 1. So transmitter put up to 1 to stop it. So here's another question you must be wondering. I mean, the data could be 1, the data could be 0. How do you know if the bit is a starting bit or ending bit, or is a data bit? How do you know that? I mean, how that works? There are zeros and ones happening all the time. How do you know that 0 is starting the conversation and that 1 is stopping the conversation? So now you need what? You need a time. Okay? So for the starting bit, it's easy because I just keep it at 1. I just keep it at 1 before I do anything. So the very first 0 will be the starting bit. That's easy, right? That's easy. It's always been 1, and now it's 0, so I know it's getting started. Okay. So what about the stopping bit? Here you have data as 1, 0s all the time, but how do you know this 1 here is going to be the stop bit? At its time, it's called baud rate, which is the transmission frequency, And the one we use for this one sometimes could be 19200, could be 9600, depending on depending on the certain tasks. Okay, so it's basically doing a count because we have a way faster clock available on the board, which is 100 megahertz. Okay, so you can use that one to count. Count to a certain count number, so we know that it's been 1 over the baud rate, which is the time. Let me ask you a question. If I'm telling you that the BPS, bit per second, okay, or baud rate is 9600. So that means you're having 9600 these little bits every second. Okay? So my question is, what is the bit width? Oh, width, 2 nanometers. That is question number, let's see, number 2, actually. Question number 2. Give it Alex, please. Alex.
Thank you.
Who else doesn't have the in-class exercise? I have it. So question number 2, for 9600 BPS, BPS means bit per second. Okay, bit per second. That's the baud rate. We'll call it the baud rate, which is something BPS, okay, for UART. And so what is the bit width?
1 over.
Yeah, it's 1 over, right? It's super simple. It's 1 over 9600. All right. So you'll know that this duration takes 1 over that baud rate. What are the 2 port names of the UART port? What are they? 2 port names? RxTX, yes. How do you put down the transmission line at the beginning and put up to logic 1 at the end? How do you put down the... that question doesn't make sense. How? You just put it down, right? Sorry. Yeah, bonus points, you know. Oh, the TX pull it down, right? TX pulls it down to at the very beginning and pulls it up to 1 at the end. Okay, and then it moves to the modules. Let's take a look at the first one first. So you will expect 4 different Verilog modules in this tutorial, and these 4 modules are the TX controller, the TX top, the RX controller, and RX top. So the RX top is pretty simple. The TX controller starts with a very standard way of doing all the states. So you want to draw the diagram first when you are looking at a Verilog module like this. So you should know the inputs and outputs first before you get into the details. So what's happening here is this is the controller block, UARTX controller. Okay, that's a digital block. And it has a send. It's just 1 bit. Whenever send is 1, it's gonna start sending. It's gonna start doing something. Okay, so data is a 8-bit. It's in parallel. This is the 8-bit data in here, and you are taking out 1 bit by 1 bit using the index to access every single bit and place it as the output. Because this is a serial, right? It's a serial communication. That means the output has to be 1 bit, right? It's a serial, it's just 1 bit. That's the whole point. You don't want to make a parallel. It's taking a lot of pin resources. It's just 1 bit doing everything, clock every single bit out 1 by 1 according to the baud rate. Okay, so that is why the output has a UART underscore TX. So that vector is just 1 bit. Okay, it's sending out bit by bit. So eventually, it's directly shorted to TX. Clock is a 100 megahertz clock. You're using that clock for the timing purposes. And ready is whenever all the data bits and parity bits are being sent out, you assert this bit, make it 1, so the receiver or the top module knows it is done. Okay, so we are looking at the module of the UART controller. Okay, according to the questions, question number 5. In the UARTX control module, why is the baud timer variable is set as 100 mega divided by baud? What is the baud parameter? It's 9600. Okay, so we set it as 9600 because we want to just make it more intuitive, right? So we know that the baud rate is 9600. However, this parameter in here is not 9600 bits per second. I mean, the parameter in Verilog like this is basically 9600. It's just 9600. It's a decimal number. Okay, it's a decimal number. So if we use this decimal number in here, and we will be able to convert this thing into the count max we want to use for the timer. And why? Why is that? So what's the what is the unit for 100 mega? 100 mega counts per second, right? It's counting. So 100 megas counts per second. So what is 9600 though, the unit? Alright? So eventually you are getting what? No. Does that make sense? It takes this many counts to finish one bit. Okay. So that becomes a count max. Okay, that becomes a count max. All right. So we want to use that one as a timer's count max. So whenever it reaches that baud timer, so the timer is counting, is ticking at 100 megahertz. And whenever this one reaches this thing, we send one bit. You can see the text data, the TX data is 8-bit. It could be 9 bits. TX data, let's see. Oh, 10 bits. So 10 bits, it has 8 bits, an error bit, and also a parity. No. No, it's a starting bit. It's a starting bit data, N bit. So totally 10 bits. So how to make that happen? I mean, we all know that the transmission starts with a 0 and ends with a 1, right? So whenever you are preparing for the package, for the TX over here, we don't have a parity here for now. Okay, just let you guys know. It's a little bit confusing. So it's basically 8 bits in the middle, and 1 0 and 1. So it put a 0 as a LSB, and it put a 1 as a MSB, and put everything as a package. So when we are sending it out, it automatically put it down because the first one is a 0, right? So the first one is getting sent out as a 0, so it pulls it down. So followed by that 0, there will be 8 bits of data, and then eventually the MSB is a 1, so sending a 1 at the end. So to make this happen, it's just so simple. I mean, to make it happen, you physically place a 0 here and place a 1 here, and put the data in the middle, sandwich it in the middle. And just send it out, right? Just send it out one by one, starting from LSB. You're sending LSB is a 0, boom, put it down, starts. Okay? Make sense? So this one doesn't have a parity bit. So it's not generating a parity bit. You can modify it to generate the parity bit. The sender, I think the sender makes a decision if the sender wants to send the parity bit or not. Right? The checker, the receiver we'll be able to receive it and eventually do the XOR and generate that parity and see if that works. So it's given that the receiver already knows the system is using a even parity checking or odd parity checking. It has to know it first. So that's question number 5. Question number 6. In the UARTX top module, line 15, the debounce, we have used it before. It's the same debounce module, just keep using it. The reason we're using debounce is because it's not because the UART requires a debounce. Okay, don't make me wrong. The UART is UART. It's a clean digital module. Don't mess with it. So once you are done with the UART digital block, keep it there. Okay. So the reason I'm adding a debounce here is because I want to put the UART controller and the debounce module in a top, and that top does some testing for us. Keep in mind, there's nothing to do with the UART block. The UART block is universal UART block. You should be able to use it anywhere else. Okay, so we are adding another debounce module and adding the button. So we are pressing the button on the FPGA board to send some signal to the computer, through USB. So if you look at the constraint file of the FPGA, there's the RX and TX ports over there, like all the J's, JB's, and all these kind of things. Same thing. So RX and TX are physical pins in the constraint file. So that is why I can do a RS TX. Okay, so RS, I don't know why it's called RS, but it's a TX port, the TX port of the FPGA. Okay, so that means this TX port is physically existing on the FPGA board. It's like something like this, right? It's the FPGA, and there's a little TX. So that TX will be shorted. You don't have to physically short it to somewhere because it's on the USB port. Your FPGA board has a USB port, right? You plug it in, the RX and TX already shorted to that USB, okay? And that USB goes to your laptop, and the TX within that USB cable goes to the RX of the desktop or the laptop, which is over here. Okay, so whenever you plug it in, you plug in your FPGA to a computer, it already builds a connection. TX, RX, RX, TX is already there. So you're not physically wiring up something, and you open up, unscrew all the screws of the laptop in the back of the laptop and trying to find out the pins, and no. So it's through USB, okay? So here's the top module, which is this bigger box over here. And we have seen this hashtag parentheses in your soft core. Remember when we are instantiating your CPU, there was a hashtag and we're changing some of the parameters in there. So this syntax, what this one does is it's replacing or overriding the first parameter or replacing certain parameters in a certain sequence. So if it doesn't show you which parameter is being replaced or overwritten, it's overriding the first one, the first parameter. So I'm instantiating the UARTX controller module, okay? And hashtag parentheses, I directly throw a number in here. And now I'm asking you which parameter is being replaced in that submodule. And why we want to do that? Why we are not directly modifying that parameter in the submodule, but instead we do it in the top. Why?
It works more like general cases, so you can have it working for like different things.
Yeah, more general cases like what I told you, right? So UART module, whenever that is done, don't touch it. It's a chip, it's the IP. Keep it there, okay? And set all the parameters you probably will change in the future as a parameter. And then you can change the parameter or override the parameter in the top, but never modify it in that chip. Keep it clean. So go to your TX controller module, which is here. Which the first parameter in here? Which one? Okay, first one. Okay, parameter baud 9600. So eventually, even though you have a 9600 baud rate in your sub module, but it's being overwritten by the top, and the new baud rate is 19200. Now let's go to line 37. What does this mean? I mean, the top is pretty simple. You can see there are only 3 states, and the third one is not really being used. I removed it and it's not changing anything. I think it's just a bit redundant because all the code is from the textbook. I don't think this makes sense. So basically only 2 states, right? So the button, whenever you press it, it's adding a 1 to the byte over here. And what is that byte? Just keep in mind, when you are sending a byte through a UART, it's being recognized as ASCII code, right? So if you are sending a byte like 41, right? 41 through the UART, it's actually sending, what is 41? Where's my UART table? ASCII table. Here. We are looking at hex, right? 41 is A. So initially, if you part it up, your top module here is just giving an internal byte. Oh, not this one. That's RX. And for TX, here. See, it's a constant. It's being put in the register. It's giving a 41, so 41 hex number to the UART module as an 8-bit parallel input, right? Parallel input, and then the UART is working pretty hard. It's taking out every single bit and send it out to the TX output 1 bit by 1 bit according to the baud rate. So it's sending a 41 first. So even at the very beginning, you are seeing an A, right? Seeing an A here. If you look at the UART port. UART terminal here. You can see an A first. Can you see that? Yeah, it's an A here first, right? And then what the top does is it receives the signal from the button. It debounces the button. Keep in mind, it debounces the button, right? Receive the press. If you press it, it's detecting a rising edge or falling edge. I should add it to the exercise. Where can I find it? If you press the button, is that the rising edge or falling edge? Come here. Circuit one stuff.
Yeah, so get the falling edge.
No.
No.
Take one more look. If you press it, falling edge or rising edge? Come on, guys.
I guess it'd be rising edge. Because when it would trigger when the button gets released, so when you press it and then release it, it would trigger?
Yeah. Typical values of these resistors, what are they? Typical values of these resistors. You guys are like, how could we know? We don't work for Xilinx. They don't pay us $150,000.
I'd probably say like 1K or 2K?
10K usually. 1K is too small for pull down or pull up resistors. So it's getting put down to 0, right? These are pull down resistors, keep in mind. So they are getting put down to 0 at the very beginning. So basically these pins are getting zeros. And you press it, this pin here is being being put up to VDD or shorted to VDD. So it's a rising edge or falling edge? It's rising edge. You press it, it's getting put up to VDD. So it's rising edge. So what are these ones? What are these ones? Current limiting resistors. So typical values. 3 to 500 ohms.
Yeah.
Okay? Make sense? Let's come back. So you know that if you press the button, you're getting a 1. Okay? You're getting a 1. Clean 1 because it's getting cleared. So press it. You press it, it's adding a 1 to it. See? It's incrementing by 1. So that's how you can get more characters from the ASCII table. Because initially it's 4-1. You press it as adding a 1, becomes 4-2, which is B. So that's why you keep pressing. It should show all the characters in a certain sequence according to the ASCII table. A, B, C, D, E, F, G, H. I'm not skipping anything, right? Yeah, it's not skipping anything, which means the debounce module is working really well. If the debounce doesn't work well, you press once, it's getting 2 rising edges. Okay, so it's gonna skip numbers. So make sure it's not skipping any numbers. And also the baud rate. Should you use 9600 or should you use 19200? Which one should you use? Definitely this one because it's already being overwritten, right? So even though some module has 9600, however, it's being overwritten. So this is the correct one that you should use. Okay? So the quiz, I'll let you take it home, and because it's open book, open notes, so you can work on it and turn it back to me probably after the break. Tuesday, Thursday, doesn't matter. Okay? I mean, the in-class exercise will be after this class. But the quiz is something else I'm going to give you in a few minutes, right?
Yeah.
20 points. Pretty good. Now the receiver. Receiver has a receiving module, also has a top with it. So a few things I need to clarify over here. Think about that. The transmitter doesn't speak English, right? The transmitter sends something and without saying anything. So the receiver will just receive it. It's just one line because TX is shorter to RX. So whenever it's getting put down, the receiver receive it, can feel it. So it sees a 0 at the receiver's receiving bit or pin. So what's the first thing it should do? Every time it should sample in the middle, because even though 9600 or 19200 is not too fast, but they are still pretty fast. It's having like 19200 bits per second. It's a lot of signals per second. It's really fast. So there will be a lot of digital signals in a very short period of time. So in that case, imagine you have D flip-flops in the receiver. So when you want to trigger that D flip-flop to latch that bit on the line to the register, when should you sample it? In the middle, at the edge, after it, before it? In the middle, right? So in the middle will be the most stable state. Okay? So what you want to do is whenever it starts, the receiver can feel it because it's the same line, okay? It sees that ground. And then start counting the same baud rate, right? It knows the baud rate and start counting. What's the count max?
Count max is, I guess like...
It's 100 mega divided by 19200, right?
Yeah.
Okay. So it counts to 50%, counts to half. Okay? And clear it for the first bit. So for the first bit, only count to the half and clear it. And after that state, you count to the full count max for the following state. So in that case, the first bit, you count to the middle, you clear it. And in the future, you count to the full count max, which will give you the bit width count. Right? Does that make sense? You do the middle first, and every time it's going to hit the middle. Okay, if you do the half for the first and full width for the following ones, so you can always hit in the middle. So it's always wait until the middle of the bit width and latch it. So if you go to the receiver module, you can see it's doing it's counting to 50% of the baud the bulk timer. That's 50%. It's divided by 2. Okay, stop there first and clear the timer and give a 0 to the timer. Clear it. Okay, and then if it moves to the next state, count to the full bit width. It's always hitting the middle. It's always sampling at the middle or in the middle. So which question is this?
Number 8.
So number 8. Number 8, right? Okay. Number 8. And did we answer number 7? Yes, we did.
Yeah.
Almost. Number 6. Yes. Okay. This is number 8. Number 9. So the receiver, it's just sending. It's just every time it waits to the middle and sample it, right? So receive that bit, so which is the bit at Rx at that line, give it to a vector, and then you increment the index. So next time it moves that new bit to the next spot. It's pretty easy. So for these ones are pretty straightforward. It's just sample that current bit and then increment your index. So next time you sample it, it's being put in the next spot. Okay, so just do it one by one. Eventually, you are getting all the 10 bits. All right, but for here you can see the count max is 8, so it's a decimal 8. Whenever it reaches the 8th, which is D7, bit 7 of the data, it moves to the check first. So the check is doing a parity check. You can see it's a bitwise XOR. It's Rx data 0 to 7 is already received and being put in this vector. It's doing a bitwise XOR and generating that 8th bit, which is a parity bit. And that parity bit is being used. It's not being tossed. So that parity bit is being put in the same vector as a bit 8. So eventually what is being received is 0 to 7, which is the data, and it's generating the parity by itself and place it at the MSB. So eventually have 8 bits as the data and 1 at the 8th at the MSB as a parity bit. All right? And also it's generating an error bit if the parity bit is not the correct one, is signaling an error as a 9th bit. Oh, 10th actually. So eventually you are having data, parity, error. Okay, which makes sense because when you receive it, you want to see, hey, is that correct? If it's not correct, then I want to see an indicator. So the indicator is the error bit. And eventually all these 10 bits are shorted to the LEDs, to the FPGA board. So eventually you are able to see it. So what's happening is you are using a terminal like this, from your laptop, and you are typing something. So you have to use a even parity checker, even parity generator. So the even and select the correct baud rate, and you start typing in there. Okay, start typing. Use your keyboard. You type 1, like you type A, it will send the ASCII code of A through this USB to your FPGA. So FPGA receiver module is able to receive it from the laptop. And receive it and throw all the bits to the LEDs. So eventually you are seeing the data here, the parity bit, the error bit, and also the count. So press 1, press A, it shows 1, it's getting received. You press another key on the keyboard, this one will count to 2. Okay, and then it's displaying that ASCII code being received at the same time, and also the parity bit and also the error bit. And normally you are not expecting the error bit to be letting up. It's pretty reliable, right? It's in the USB. Otherwise, you have to contact the Dell, right? What's happening with my laptop?
Yeah.
So this should be always off. If there's some like radiation or RF signals, noises probably will flip a bit, but usually it shouldn't. Okay. So press something, it's going to show up over here and also show the parity and also show the. It's basically in your Verilog, what you did is you do a bitwise XOR for all the bits being received, and then it's generating the parity bit. So it's really simple. And error bit as well. Okay. So test a few different examples. See if that works. So basically, this tutorial shows you how to do a communication from your IPGA to the laptop by pressing a button on the IPGA board. Okay, so you press it once, it increments starting from 4.1, which is A, right? You are sending ASCII code from the IPGA to your serial. You can use the Arduino one, you can use a different one, doesn't matter. So you are seeing that display in the serial terminal. And the second experiment is on the receiving mode. So the IPGA is receiving instead of transmitting. So receiving things from the laptop, you type, you press the keyboard keys and send ASCII code to the IPGA board. It's receiving and trying to display. It doesn't have any other display mechanism, so it has to be the LEDs. You're gonna make it more complicated. You can use a 7-second display, but you don't have to. I mean, just LEDs. Okay, so it's bi-directional. Press display. Press display. Okay. Did you answer the last question? No, not yet. So number 9. RX top. Oh, I did actually. RX top. Let's take a look at it.
Yeah, those are the LEDs you're talking about.
Yeah, so here, right? 22. What is this one doing?
It's basically receiving. It's basically displaying the signal that you're showing on. Well, I guess no. That would be what LEDs 90 are doing.
Yeah, every time it do a concatenation like this, right? So this is the data. The parity is the error, remember?
Mm-hmm.
So we directly throw these bits, the 10 bits to the LEDs. This 10 bits, 8 bits of data, 1 bit of parity, 1 bit of error. Remember on the LEDs?
Mm-hmm.
Like this. Data, parity, bit, right? And for the rest, we use them as what? As a count. So every time we do one concatenation, we throw it to the LED, we count by 1. It's counting. Five minutes to finish the quiz.
Okay. Oh, actually, I was gonna ask, can you know these wires, these mystery wires that were in the drawer from the LCD project?
Yeah.
Do you want this? It doesn't matter.
Yeah, and you can turn it back to in 602 labs. There's a box that has these wires.
Alright.
This has so we can just sort it.
Alright.
And also return your LCD parts. Have it here.
Actually, it is what is counting by 1 for the last question?
The counts of data being sent.
Oh, okay.
Let's put it here.
And the data can be 8 bits most.
Mm-hmm. Bytes, right?
Bytes.
Data's always in
Hey, point one is not. So 9 questions. 9 times 0.1.
0.9 total.
I need it.
Put these wires away.
Don't have spare wires?
Not anymore. Well, back in my dorm. It just reminds me of like there were some LCDs.
The other one is the take-home quiz.
Just place it there. I will find a box. No worries.
Okay.
I'm gonna go work on my finish my layouts and it's easier.
quiz is.
Take hold, please.
Oh, thank you.
That's because he spent 8 hours on it. Yeah. Stayed till like 9 p.m.